Right, in this session we make a little bit of history in the sense that we start our first serious theorem with its proof, and it's challenging and complicated enough that Sipser starts, here's the first time, providing a proof idea. Okay, so instead of just plunging straight into the proof as we have done in the past in earlier sessions, the proof now is long enough and complicated enough that it's easy to lose sight of the big picture. You get bogged down with details and you forget where you're going. You're so busy racing ahead that you sort of forget which direction you're supposed to be going. That kind of thing. There's an expression in English for that. You can't see the wood for the trees. Now, wood in the sense it's not like it's not this kind of wood, right? It's wood. It's wood in the sense of forest. Meaning, if you stand too close to a large tree with say a wide trunk, right, then you will not be able to see the forest. You will not be able to see the other trees. Okay, so by analogy, you're standing too close to the details of something, and you don't see the big picture. Right? That's what the expression is about. Not seeing the wood, in other words, the forest, not seeing the wood for the trees. Okay. You're too close to the trees to see the whole forest, the whole wood. Okay, so hence the idea of Sipser to provide before you get into the detailed proof, to give a proof idea, a sort of overview, the big picture of the proof, which is helpful. Because these proofs can get quite long and complicated, several pages of proof sometimes. So okay, so that will be his pattern pretty well from now on. Now tonight I will do a bit of homework myself and actually find, I think per chapter, I think I may as well do it by chapter, how many theorems there are for each chapter, and then I'll add them up. To find how many theorems there are total in this textbook. I'm suspecting the answer is going to be over 100, somewhere between 1 and 200. That's my guess. I'll tell you next board. All right. Okay. So here's the beginning, the first example of his pattern, his way of providing proofs. His format for proofs. Will be typically theorem ID, some numerical ID for the theorem. So this is theorem 1.25. The 1 refers to the chapter number. So we're in chapter 1, whose topic is regular languages. Okay. The 2.5. What does that mean? It's the 25th thing that he has ID'd in that chapter. Now that thing could be a theorem, an example, a corollary, a definition, whatever, right? So and he just has all these things and he just numbers them in sequence. It's what I call global ordering, which is very useful when you come to find, like imagine in some proof, and you'll see some comment as was shown in theorem 0.14. And so you go back to chapter 0 and you look for item, whatever it was, 1.4. Now if it were like theorem 1.4, so you go looking for the 14th theorem, then you may have a hard time finding it, because if the numbering is according to the type, like is it a theorem or is it an example and so forth, then you've got to it's much harder to find that where the link refers to than if you're using global ordering, what I call global ordering. So with global ordering, if you see something or other 16, well then you know you only have to go back two slots, if you like, 2 steps, to get something 14. And if it's theorem 14, well then you've found it. So global ordering is pretty commonly used now. But for example, last night reading a theory on a book on complexity theory, where the global ordering is not used. So the author is using, like, we'll refer to theorem 28, and it's the 28th theorem in some chapter. But it's all mixed up with definition 14, and that's the 14th definition in that chapter. So if you want to find example number 9, it's all, where's the 9? Because it's all mixed up with the numbers of different theorem numbers. It's a mess. So it's just easier with global ordering. And Sipser does use global ordering, thank God. So it's easier for you to find other theorem numbers or example numbers, or when there's a link to some other thing, you can find it easily, because you just find the numerical order to find the item that's numbered using global ordering. And if you're not clear what that means, is if you have the text and you're using it and you're referring to other things that get linked to, you'll find those other things more easily with global ordering than the alternative older system that people are learning or have learned to give up. And I do notice correlation. Europeans are a bit more conservative this way, less likely to use global ordering than the Americans. That's my impression. All right. Okay. So chapter 1.25. So that's the 25th item, whatever it is, whether it's in this case it's a theorem, or it could be an example, or a corollary, or a definition, or whatever. And the 25th thing in this chapter that you label, that you give a numerical ID to, right? And then, so an ID, and then the theorem statement. And if the theorem's not trivial, typically Sipser will give then a proof idea. He calls it a proof idea. And then after the idea, sort of an overview, the general strategy of the proof, if you like, the main features of the proof, then he'll give the detailed proof, the same proof, but so he will flesh out, so to speak, this overview proof. So in a sense he provides 2 proofs. One is the overview, and the second one is the details. Okay? So expect that from him now for the rest of the book. Right? It's a general pattern for the whole text. Okay, so this is our first example of it. So a little bit of history. Okay. All right. So here's the theorem ID, and here's the statement of the theorem. So the class, like the family, the set of, if you like, of regular languages, is closed under the union operation. And what's that's saying is take any 2 regular languages, and any 2 of them, and union them. So say A1 union A2, the result will also be a regular language. That's all it's saying. That's what that's saying. Okay. So that is, i.e., that is, if A1 and A2 are regular languages, just any 2 regular languages. In other words, there's an automaton that recognises that one. There's an automaton that recognises that one. By definition, that's what a regular language is, right? You know that. Okay. So you have any 2 regular languages. You union them, and the result will also be a regular language for any 2. In other words, that's closure, right? That means when the result belongs to the same set as the things that you operate on, well, that's closure. So in other words, the union operation, the class of, the set of, the family of this. Why do I use the word class and not set? Interesting question. Okay. Now here they're using class, and else they used, what was another term? They had another term, I'm trying to remember what it was. Well, anyway, okay. So, so the class of, or the set of regular languages, it's closed when you union. The operation union will give you a result that is also a regular language. That's the statement of the theorem. Okay. So